Welcome to Lecture 5, Section 2. This PowerPoint will cover 5 Laplace transform examples. You may want to make sure that you have your Laplace transform table, which are on pages 5-5 and 5-6 in your course packet. And welcome to Lecture 5, Section 2. This PowerPoint will cover 5 Laplace transform examples. You may want to make sure that you have your course packet with you so that you can refer to page 5-5 and 5-6, 5-7, and 5-8. The examples presented in this video go over the first 2 steps of the 3-step process to use Laplace transforms to solve differential equations. We're going to find the Laplace transforms and solving for Fs. And we will talk about taking the inverse next week, which is the 3rd step. Here we have the time domain expression ft equals 3 plus 2t minus 4t squared as our first example. The first step is to find the Laplace transform of the expression. We will do it term by term. The Laplace expression of ft is capital Fs based on equation 1 in the Laplace transform table. Next, we transfer the first term on the right side of the equal sign, which is the constant 3. To find the transform, we go to the middle column of our table and find the line that corresponds to a constant. As we go down, we find equation 6 in the Laplace transform table, and a equals 3 in this case. The corresponding Laplace transform is in column 3 and is 3 over s. The note in the table also tells us that this corresponds to a step change. The Laplace transform of the second term, 2 times t, is found the same way. Search through column 2 to find the expression with the constant times 2t. Equation 8 is the correct time domain expression. The corresponding Laplace transform for a times t is a over s squared. In this case, a equals 2. So the Laplace transform for the second term is 2 over s squared. The note indicates that this is a ramp function. The Laplace transform of the third term, 4 times t squared, is going to require us to use 2 equations to complete the transform. We will use equation 14 and equation 3. Equation 3 tells us that a constant times any expression is the constant times the Laplace transform. Equation 14 tells us that the Laplace transform of t squared is n factorial over s to the power of n plus 1. In this case, n equals 2. So the expression is 2 factorial over s cubed. And 2 factorial is 2 times 1, which equals 2. Then, applying equation 3, we multiply the result by 4. So we get 4 times 2 factorial over s cubed. The second step is to solve for Fs, which is not needed once we make the substitutions after completing the Laplace transform. Fs equals 3 over s plus 2 over s squared minus 8 over s cubed. We used equations 1, 6, 8, 14, and 3 to complete the transformation. It is strongly encouraged that you note which equations you use in your homework. Here, we are given the time domain expression ft equals 2 times cosine 3t minus 4 times sine 2t as our second example. Our task is to take the Laplace transform and solve for Fs. The transform of ft is Fs, based on equation 1. Next, we go through the middle column of the table to find sine and cosine expressions. We find them in equations 9 and 10. But equations 9 and 10 don't have constants multiplied by the sine or cosine, so we need to apply equation 3 again. Using equations 3 and 10, we find that the Laplace transform of 2 times cosine 3t is 2s over s squared plus 3 squared. And similarly, we can get 4 sine 2t to be 4 times 2 over s squared plus 2 squared. we used equation 1, 3, 9, and 10. Using the four transforms means that the Laplace transform of the time domain expression ft is fs equals 2 times s over s squared plus 9 minus 8 over s squared plus 4. For these first two examples, we didn't need to solve for fs because the term was by itself on the left side of the equation sign. That is not always the case though. So here we have a third example. In this example, we have derivatives in the expression. As before, we will transform the equation term by term. When we take Laplace transforms of equations with derivatives, we need initial conditions at time t equals 0. In this case, they are all equal to 0. That will not always be the case. Example 4 is not in the class notes. In the past, we used this as a class activity question. Find the Laplace transform xs, given this equation shown here. We have up to a second order derivative term and a cosine term. Again, to solve such an equation, we use the Laplace transform from term to term. For the second order derivative term, we get s squared times xs minus s times the time domain function at time 0, which is x0, minus x0 prime, which is the first derivative of x at time 0. And similarly, we can get the other terms. And also, we are given the initial conditions as x0 equals 1 and x0 prime equals minus 1. By inserting the given number, we can clean up each term. And in the end, when we combine all the terms, we get the expression shown here. Now we solve for xs and get the equation shown. The final example is zt equals t cubed times e to the power minus 8t plus e to the power minus 5t times sine 7t. Again, to solve such a problem, we will transform each term using equations in the table. For the first term, we have the Laplace transform of zt to zs. And for the second term, we use equation 17. And for the third term, we use equation 25. And when we combine the terms, we get the expression for zs. In this case, we do not need to use algebra to solve zs because it is only in the first term. This ends the example problems demonstrating how to transform time-dependent equations into Laplace domain equations using Laplace transform and solving for fs based on the tables that you can find in the course packet. If you have any questions, please write them down and bring them to class to discuss.